Good morning. Myself Nancy from Chemistry Honors BSc first years making video on inorganic chapter number 2 periodic property. The concept of periodicity has acquired the key position in the study of inorganic chemistry. No other generalization competed the periodic table of element in its ability to simplify the systemize and rationalize known as chemical facts. At present, about the 118 elements are known, which has been numerous property and follow from the million of compound. The periodic classification of the element have extremely simplified their study. Many different form of the periodic table has been proposed depending upon the purpose for which the table is used. However, the most commonly used form is known as long form of periodic table. Let us verify the repeatable development of periodic table and its silent feature as already studied in earlier classes and important periodic property and their application. Development of periodic tables. Since the beginning of 19th century, scientists has been trying to find the basics of grouping the element having the similar property through the several scientists, namely Loris, Dobler, Newland, Meyer, Mendel, attempt to find a certain regularity among the element. The first important attempt to divide the element on the basis of physical and chemical property was made by German chemist Luther Meyer and a Russian chemist Dimitar Mendel. They observed that when the elements are arranged in order of increasing atomic weight, the element with similar property reassure at regular interval. The Mendel gave a law known as periodic law. The law states that physical and chemical property of element are periodic function of the atomic weight. Mendel's classification gave him so much confidence that he boldly left certain space or gap for undiscovered element. By considering the property of the adjacent element in his table, he predicted that the property of these undiscovered elements later on, when these elements were discovered, their property were found to be actually similar to the predicted by the Mendel. For the example, gallium, germanium were not discovered at the time when the Mendel formulated his periodic table. He not only predicted the extent of these elements, but he also estimated their property. He named these elements as an eka aluminum, eka silicon, because he believed that these would be similar to aluminum and silicon respectively. When the chemists discovered these elements, Mendel's prediction of their property proved to be remarkably correct. Modern particle law. In 1912, Mossel showed that the physical and chemical property of the atom of the element are determined by the atomic weight and not by their atomic weight. This extension of the atomic number as important characteristic of atom lead to be modern periodic table, which is stated as the physical and chemical properties of a element are periodic function of the atomic number. Constantly, when the elements are arranged in order of their increasing atomic number, it is observed that the element of similar property ratio to regulate interval as periodically as regulate of these the element fall in certain group and lead to be arrangement called periodic table. With the modern periodic law as the guidelines principle, many new form of the periodic table has been proposed. However, the general plan of the periodic table has been remained the same as proposed by the Mendel. On this, the most commonly used form is known as long form of the periodic table. The long form of the periodic table, position of element in the periodic table. Mostly while use the periodic table these days is long form of the periodic table. This is constructed on the basis of repeating the electronic configuration of the atom, which they are arranged in order of increasing atomic number. Long form of the periodic table is given on the text page. Structure feature of the long periodic table. The long form of periodic table consists of horizontal row called period and vertical column called group. They are discussed below. Period. A horizontal row in the periodic table is called period in terms of electronic structure. Electronic structure of the atom. A periodical consists of series element whose atom has the same number of shell. There are 7 periods and each period starts with different principal element of first period. The first period corresponding to n is equal to 1 is unique because it contains only 2 elements, and this is not surprising because the first shell has only one orbital which can accumulate only 2 electrons. This means that there can be only 2 elements in which one and two electrons are present in the first energy level. The first period contains the hydrogen and helium element of second period. The second period contains 8 elements because the n is equal to 2. There I have 4 orbital 1 and 2 s and 3 2p. In all these, the 4 orbital has a capacity of 8 electron, and therefore the second particle has 8 element in it. It starts with lithium 2 in which one electron enter the 2s orbital, and the period end with neon in which the shell is completed by 2s to 2p6. The element of third period corresponding to n is equal to 3 has 9 orbital and 3s 1 3s 3 3p and 5 3d. However, their energy diagram for multi-electron atom that 3d has higher energy than the 4s, and corresponding 3d is filled with after filling of the 4s. Hence the period involved filling of 4 electron only 4 orbitals and containing the 8 element. The element of fourth period corresponding to n is equal to 4 involve the filling of 4s and 3 1 4s and 3 4p orbital. 4D and 4F are higher energy than the 5S are filled later. In between the 4S and 4P, 5 and 5 3D orbital are filled in which the energy in between these elements these between these orbital tucks in all the 9 orbitals are to be filled, and therefore they are 18 element in the fourth period from the periodic table. From potassium element of fifth periodic table. The fifth periodic table, like the fourth, also consists of 18 element, and being from rhodium will be filled to the 5s orbital and add to be xenon will fill up to the 5p. The element of six period contain 32 element, and successively electron enter into 6s 4f 5p 6p in that order. It start with cesium and end to the radon. The element of seventh period contain 32 element, and successively the element enter into 7s 5f 6d 7p orbital and start with a fixing and an organizer, and these elements are radioactive element. This also provide a theoretical adjustment for the periodicity occur at regular interval of 2, 8, 8, 18, 18, 32. This number 2, 8, 18, 32 are called the magical number. The first three periodical contain 2, 8, 8 elements respectively are called short period. Next three period containing 18, 18, 32 elements respectively are long period. Group. A vertical column in the periodic table are known as group. In terms of electronic structure, the atom a group constitute a series of elements whose atoms have the same outermost electronic configuration but have a different number of total electrons. There are 18 groups in the long form of periodical table. According to the new recommendation of Institute Union of Pure and Applied Chemistry, the group are numbered from 1 to 18. Previously, there will be from 1 to 8 as A B group. Both the system of numbering and the group are given in the periodical table. However, the old constant is still used in many books. The first group of the extreme left and last six group on the extreme right hand involve the filling of s and p orbital respectively. These groups represent the main group of the periodical table and are numbered as 1 to 13, 14, 15, 16, 17, 18, corresponding to configuration of NS1, NS2, NS2, NP1, NS2, NP2, NS2, NP3, NS2, NP4, etc. respectively. In older system, these are denoted as the first A, second A, third A, fourth A, fifth A, sixth A, seventh A, or zero respectively, corresponding to the general configuration of NS1, NS2, NS2, NP1, and etc. These elements are present in these group are known as normal or representative element. The first three periods contain 288 electron involve the filling of s and p orbital, but the fourth involve the filling of 3d orbital also. And these result in 10 more group there. These 10 group lie in between the first two and last six group. Between this group 2 and the group 13 become 3D orbital are filled after the 4s. There is 4p and there is usually labeled as B group. These elements present in this group are transition element. The name is derived from the fact that they represent transition in the character from the reactive metal. On the other side, the non-metal, there are the more row at the bottom of the product table. The row are consists of 14 elements after the lithium and the 14 element which follow the actinium. They are placed separately to avoid their induced sideway explanation of the vertical table. The limitation in the first row strain from the limitation are called longitude, and element present in the second row strain from the acronym called the actinoid. These actinoid and actinoid together are called inner transition element and rare earth metal, hence is built up of the flowing F orbital. It is important to note that the formed above discussion that the first two group, the last six group, and 10 in between these two extreme, and 14 small group at the bottom of periodical table corresponding to maximum number of electrons which may be added to p, s, p, d, f orbital respectively. Discovery and nomenclature of element with the atomic number are more than 100. The number the first scientific attempt to prepare the element behind the uranium made by the Econia Ferris and co-workers in 1934. The radiation of uranium with the slow neutron and found several radioactive products which were found to be due to new element. This constitute effort of the scientists lead to be new element, and these are called transneutron element. Today we have element up to 118, and these elements were earlier named as transitional by its discovery or discovered. However, after some time, despite regarding the original discovery of some plant at atomic number 104 above which the have arisen after several years of discussion by the communication in nomenclature of inorganic chemistry and the cons- comment on the chemistry around the world. IUPAC in, in the 1997 recommended a nomenclature for official name of the new element until their name are officially recorded, and this nomenclature is based on the Latin work for their number, for example nil, 0, and 1, and so on. The name of the derived by the combination together root in the order of digit which make up the atomic number, and IUM is added at the end. For example, the atomic number 104 is named by directing un plus nil plus quad is unnil quadrium. Classification of element into SPD block. The long form of periodical table can be convertible divided into four main blocks. In this division, the elements which involve the filling of particular orbital are grouped together as shown in figure first. First, S block, the element in the last electron enter in S orbital of their outer energy level is called the S block element. It consists of the element of group first, second, having the ground state electronic configuration of outer shell NS1 or NS2 respectively, where the N stand for the outer energy cell. The element corresponding to NS1 configuration are called alkali metal, and while those who are corresponding to NS2 configuration are called alkaline earth metal. Thus, generally, the general electronic configuration of S block element may be expressed as general electronic configuration of S block is NS1 and 2. P block element, the element in which the last electron enter into p orbital of their outer energy level is called p block element. The element of the group third A to 8A involve addition of 1, 2, 3, 4, 5, 6 respectively in the p orbital, and s are already filled by the atom consist the p block. Generally, electron configuration for the atom of this block is written as ns2 np126. D block element, the element in which the last electron enter into d orbital of the but one of the energy level consists of the element. This block can consist of the element lying between the s and p block start from 14th and onward. This constitute from 3rd B to 8th B and 1B and 1 2B in the periodical table. In these element, the outer shell contain 1 to 2 electron in their sp orbital, but the last electron enter the last one and the shell. The general electric configuration for the atom of D block may be written as n-1 D 1 to 10 and 1 or 2. There are also the transition, they are also called transition element. The transition comprise the following 10 element. These rows are called first, second, third, fourth transition series, which involve the filling of 3D, 4D, 5D, 6D respectively. These series of transition element are called transitional series. The first transition series is cadmium to zinc, second from deuterium to cadmium, and third from lanthanum to mercury, and fourth from actinium to copernicium. The F block, the element in which the last electron entered the F block of their atom are called F block element. In these element, the last electron is added to the third to outer called the enter Patiriamate energy level n minus 2f. These consist of two series of elements placed at the bottom of the periodical table. The first series called Latinium and the element are represent called latinoids. These are also called rare earth metal. The second series follow the actinium and these are called actinides. They are also radioactive in nature. Journal electron configuration of the F block element may be written as n minus 2 f1 to 14 n minus 1 d 0 to 1 and n s2. For example, for the latinoid, the general configuration is n 4 f1 to 14 5d 0 to 1 6s2, while the actinoid is 5 F1 to 14 6 0 to 1 7s2. The elements included in this series are called inner transition element because they are transistors within the transition transition element of the block. Cause of periodicity. The resume smaller property of element after certain regular interval when they are arranged in the order of increasing atomic number are called periodicity. Classification of the element in the certain families was based upon the observed similarity in the physical and chemical property. But why do the certain element exist similar property and why do the similar property rare in regular interval of atomic number, where some important question may be answered? We know that the atom consists of nucleus surrounded by the electron. In ordinary chemical reaction, the nuclei of the atom do not undergo any change, and therefore it is the distribution of the element. Further, it has been also found that the property of the atom do not depend on so much on the arrangement of the electron in the inner shell. Thus, it must be primarily be the arrangement of the electron in the outermost shell that determines the property of the atom. For example, the electronic configuration of the atom alkali metal in the group to show that they are also one of the electron in the s shell and s orbital of the flowing outermost valence produced by the noble gas configuration. The general electrical configuration of these may be written as noble gas NS1, where N stands for principal quantum number. The cause of periodicity of the property of element is the repetition of similar electronic configuration of their atom in the outer energy shell after certain regular interval. Periodic Periodic properties. There are many physical and chemical properties of element which show the periodic variation with the atomic number. Some of these properties such as valency, atomic size, ionization enthalpy, electron affinity are directly related to the electronic configuration of the atom, while the properties such as melting point density are indirectly related to the electron configuration. First, atomic radii. This is very important property because many physical and chemical property are related to atomic radius. Generally, in term, atomic radius means the distance from the center of nucleus to the outer shell of electron. If the atom is assumed to be spherical, its radius is spherical. However, absolute size of an atom is difficult to define because of the following reason. According to the probability feature of electron, an atom does not have well-defined boundary. The probability of finding the electron is never zero, even at a large distance from the nucleus. It is impossible to isolate an atom measure its radius. The probability Distribution of an atom is also affected by the presence of atom in its neighborhood. Therefore, the size of atom may be changed in going from set of environment. Thus, we can only ultimately define atomic radius as an effective size, which means that the distance of the closest approach of one atom to another atom is given by bonding situation. In another word, the atomic radius corresponding to limited of approach another atom in a particular substance. Therefore, the atomic radius may be called covalent radius, van der Waals radius, ionic or crystalline radius, depend upon the type of bonding. First, covalent radius. The radius of atom is calculated by measuring the distance between the center of two atoms in a molecule, which help of X-ray diffraction or a special study. In the case of homologous diatomic molecule, the atomic radius is defined as one half of the distance between the center of two similar nuclei bound together in a molecule. The radius is called covalent radius because the homonuclear diatoms are held together by a covalent bond. For example, the internuclear distance between H2 molecule is atomic radius of hydrogen is 0.74 nanometer by 2 is equal to 0.37 nanometer. Similarly, the atomic radius flow of fluoride, chloride, bromide are 0.4, 0.99, 1.14 respectively. And because the internuclear distance of F2Cl2 Br2 are 1.28, 1.98 and 2.28 respectively. In the case of heteronuclear diatomic, it has been observed that when the covalent radii of different atoms joined by a single covalent bond are added, the resultant value fairly well will with the experimental determination the internuclear distance of that molecule. For example, the internuclear distance of HCl molecule can be calculated by adding the atomic radius of H and Cl. The calculated value of the internuclear distance is a good arrangement with the experimental observed internuclear distance of 1.13 nanometer in HCl molecule. This is a process may be reversed. The atomic radius of H atom may be calculated by stretching the atomic radius of Cl from the internuclear distance of HCl molecule. In general, the atomic radius of the atom B in a AB molecule can be calculated by measuring the internuclear distance of AB molecule and known atomic radius of A as RB is equal to RAB minus RA. Diatomic radius of an atom do not form diatomic molecule with single bond are calculated by indirect method. For example, the single bond radii of nitrogen and oxygen are not obtained by the bond length in NO2, and because these molecules contain multiple bonds, one half of the intermolecular distance of the molecule will be corresponding to the multimolecular radius. For example, triple bond of radius nitrogen is 1.10 by 2 is equal to 0.55 meter, and the single bond atomic radius of nitrogen can be obtained by indirect method of compound in which an atom is bound to the another atom by a single bond is selected. For example, the intermolecular distance by the Cn in the H3CnH2 has been found at 1.47 nanometer. Since the atomic radius of carbon is 0.77, the obtained by the CC bond distance in the diamond, and the atomic radius of nitrogen is 0.70. Multiple bond radii. The multiple bond atom of the corresponding radii are called multiple bond radii. For example, the carbon has a double bond of radius 0.66 centimeter in ethylene and the triple bond of the radius of 0.60 in acetylene. The carbon has single bond radii of 0.77 in as in the ethane. Similarly, nitrogen has single, double, and triple bond radii of 0.7, 0.6, and 0.55 nanometer respectively. As a number of bond length increase, the attraction between the atom also increase, and therefore the atom approach closer and atomic radius decrease. Hybridization and atomic radius. The state of hybridization also affect the radius of an atom. For example, carbon hydrogen single bond in methane and ethylene and acetylene is different. Therefore, the atomic radius of the carbon is different. For example, CH intermediate distance are CH4 in methane is 1.14, in ethane is 1.1 nanometer, and in ethine is 1.07 nanometer. Since the atomic radius of hydrogen is 0.37, the atomic radius of the carbon in CH4, in methane, ethane, and ethylene is 0.77, 0.74, and 0.70 respectively. Decrease in atomic radius of carbon hydrogen bond intermolecular distance may be also be attributed to increase the s character in going from sp3 to sp2 and from sp, which increase the s character. The electronic pair between the carbon and hydrogen become closer to the nucleus and result in great attraction. Therefore, atomic radius decrease. We have been learned that the atomic radius is depend on many factors such as bond order, bond type, oxidation number of the atom, crystalline structure, which make the comparison. We keep in mind that we can compare similar type of radius atom in a row or group. Atomic radius of an element of sp element give in table 3. Metallic or crystal radius. This gives the size of atom in case of metallic element. In the case of metals, a large number of atoms are closely packed and held together by a mean metallic bond. The closely packing of the metal atom are known as crystallic lattice or metallic lattice, and the packing in different metals. The metallic radius is defined as one half of the distance between the nuclei of the two adjacent atoms of metal in a metallic lattice. The intermolecular distance between the nearest neighboring atom in a metallic crystal is determined by X-ray diffraction. This is divided by 2 to calculate the metallic radius. R metallic internuclear distance between two adjacent atoms in a metallic lattice divided by 2. For example, metallic radius of the sodium is 1.86 nanometer. The metallic radius are larger than the corresponding single bond covalent radius. For example, the covalent radius of the sodium is 1.54 while the metallic is 1.86 nanometer. This is because the metallic bond is weaker than the covalent bond, and therefore metallic atoms in the lattice are known down as to be closer to each other as is in the covalent. Van der Waals radius. Van der Waals is defined as one of the radius of internuclear distance between the two adjacent atoms belong to the nearest neighboring molecule of the same substance in the solid state. It has been observed that there are some weak force of attraction between the neutral atom of noble gas atom and non-polar molecule of the various substance. They are also known as van der Waals forces due to the force of noble gas atom and the non-polar molecule are held together, particularly in a solid state. This van der Waals radius corresponding to the closest approach of two atoms of noble gas or the non-polar molecule of another substance which otherwise do not form bond. The measurement of the van der Waal radius of chlorine is given below in the figure third. Thus, the radius of van der Waal is equal to internuclear distance between two non-bonded nearest neighboring atom by 2. The internuclear distance between two chloroatom of nearest neighboring molecule is equal to 3.6 nanometer, and for the van der Waal radius of chlorine is equal to 3.60 divided by 2 is equal to 1.80 nanometer. The van der Waal radius of the sum of the given in table 4 among these the covalent radius as the evidence that from the table 4 the van der Waal radius are larger than the covalent radius, and this can be observed because in the formation of covalent bond the atom came closer to each other due to overlapping of orbital. On the other hand, van der Waal exists between atom or molecule are weaker, and these are on the other hand van der Waal exists between two atom and molecule are weaker and are at large distance. Therefore the internuclear distance in the case of atom held by a van der Waal force is more than between the covalent atom. Consequently the van der Waal are larger than the covalent. Becker-Steller radii. Becker and Steller processes get internally consist atomic radii. These radii can be added in respectively of bond type involved in interaction between two atoms to give the good correlation with observed internuclear distance. In general term, the Becker and Steller radii represent the radii of inner core of the electron, which term determine how closely the two atomic species can be approach each other, and Becker stellar atomic of the nuclear of second period are given ahead. Periodical trend in size. Let us discuss a periodic trend in period or a group. Variation of atomic radii in period. In generally, the atomic radii decrease as we move from left to right in a period in a periodical table. For example, in the second periodic radii decrease from lithium to fluorine through Be beryllium, boron, carbon, hydrogen, oxygen as given in table. Explanation: this may be on the basis of increasing nuclear charge along a period. With increased atomic number, the lithium or to fluorine, the magnitude of the nuclear charge increase, while corresponding adding the electron take place in the same principal cell. Since the electron in a search cell do not screen each other for the nucleus, the increase in nuclear charge is not neutralized by the extra valency electron. As a result, the electrons are pulled closer to the nucleus by increasing the effective nuclear charge, and therefore cause a decrease in size of the atom. In this way, the atomic size go on decreasing across the period. Variation of atomic radii in a group. The atomic radii of the element increase from top to bottom in a group. Explanation: in moving down the group, the nuclear charge is increased with increase in atomic number, and we can accept it that the size of an atom should be decreased. However, while going from one atom to another, there will be increase in principal quantum level, and although the number of electrons in the outer shell remains same, the effect of increase in size of electron could be more pronounced than the effect of increased nuclear charge. Consequently, the distance of the cloud is more pronounced than the effective increased nuclear charge. Consequently, the distance of the outer electron found the nuclear greatly increase down a group. In another word, the size of the atom go on increasing. We can move down a group and isolate to table 6 for the alkali metal group. It is clear from the above figure that the alkaline metal atom are at maximum of a plot, halogen atom are at minima, and the value of for the noble gases are not plotted because they corresponding to van der Waal radii. This showed that the largest atom in any period are alkali matter and the smallest are halogen, ionic and crystalline radii. The ionic radii corresponding to the radii of iron in a crystal, and the iron are formed as a result of addition or removal of the electron from the outer shell of the atom. The ion formed by the loss of electronic wire positive charge are called cation, while the ion formed by gaining of electronic wire the negative charge are called anion. Ionic radius may be defined as effective distance from the nucleus of ion up to which it can be influenced the ionic bond. Measurement of ionic radius. The X-ray study gives the distance between the nuclei of adjacent positive and negative ion in the crystal. If the ions are regarded as pair, the internuclear distance may be taken equal to the sum of radii of the cation and radius of an ion. For example, the internuclear distance of Na plus and Cl negative is 2.76 nanometer, which is corresponding to the sum of ionic radii. But the problem of assigning the different value to constituent ion is not simple unless the radius of any one is known. We cannot be calculate the radius of other ions. Several method has been proceeds to calculate the ionic radius of ion. Out of these method, pooling method is usually accepted. Pooling method to calculate the ionic radius. This method is based on calculation of ionic radius from the observed internuclear distance from a set of ionic compound which has the cation anion isoelectronic. Their cation and anion has the same number of electron. He selected four ionic compound NaF, KCl, Rb, Br, and CSI in salt. The cation anion are isoelectronic. For example, NaF, both the Na and F have the 10 electron has a configuration 1s2, 2s2, 2p6, and similarly the KCl and Rb, Br, and CSI the anion cation have 18, 36, and 54 electrons respectively. Pooling suggests that from the isoelectronic ion, the radius of an ion is inversely proportional to effective nuclear charge of the cation. Is R is equal to C by Z minus S, where C is proportional constant. It can be for the two isoelectronic ion. Therefore, the effective nuclear charge can be by separating a screen constant from a actual nuclear charge. The value of screen constant is calculated from the Stellar rule. Let us consider an example of sodium fluoride. The internuclear distance in the NaF has been calculated by 2.31 nanometer so that the R radius of Na plus radius of fluoride is equal to 2.31 nanometer. Both the Na and F are isoelectronic and has the same value of screening constant. According to the stable rule, the screening constant for both the ion has been found to be 4.15. So S is equal to 4.15. The actual size of the Na and FCl is 11 and 9 respectively, so that the internuclear force charge is 6.85 on sodium and effective nuclear charge on fluoride is 4.85. According to Parents' rule, we can substitute the value and we find that the radius of fluoride and sodium is 0.96 and radius of fluoride is 1.33 nanometer. With the help of the above production, the radius of the cation anion has been determined. Size of cation and anion. The size of cation in general is the size of cation is smaller than the neutral atom. This is due to the fact that the removal of electron from an atom, the magnitude of the nuclear charge remain constant. Same, while the number of electrons decrease, as a result, the nuclear charge now act as lesser number of electrons. In the another word, the effective nuclear charge per electron increase and the electrons are more strongly attracted and pulled toward the nucleus and cause a decrease in size of atom. Example दे रखे हमें the size of the cation anion. In general, the negative anion is always larger than that of corresponding atom. The negative charge is formed by gaining of one or more electron in the remain in the neutral atom have increased while the magnitude of the nuclear charge remain the same. As a result, the same nuclear charge act on the large number of electrons than present in the neutral atom. In another word, the effective nuclear charge per electron is reduced and the electron cloud is held less tightly by the nucleus. This causes the increase in size and thus anions are larger in size than the corresponding atom. The ionic radii of the sum common of sp and p block element are given in table 7. Isoelectronic species. The isoelectronic species are the anion of different element which help have the same number of electron but have different from one another in magnitude of the nuclear charge. A set of species having the same number of electron are called isoelectronic species. For example, the species of anion, all the species has the 10 electron. Periodical trend in ionic radii. First, the ionic radii in period. For the isoelectronic series, anion has the same number of electrons. The ionic radius increase as the nuclear charge increase. Explanation: an isoelectronic series that has increase in nuclear charge, therefore the attraction of the same number of electronic charge increase. As a result, the electrons are pulled more and more strongly, thus the ionic radius decreases. All above known confusion contain 10 electrons. Second, ionic radiation in group. As we know down the group, the ionic radii decrease with decrease in atomic number as shown in figure table 9 like the atomic radii. Explanation: this is mainly due to the increase in principal quantum level. The effect of the increase in principal quantum number is more pronounced than the effect of increase in nuclear charge. Explanation: this is mainly due to increase in the principal quantum number level. The effective increase in principal quantum level is more pronounced than the effective increase in nuclear charge. Ionization enthalpy. Ionization Ionization energy. The ionization energy gives a measure of days with which an atom can lose an electron and change into a cation. Ionization energy of element is defined as the amount of energy required to remove the most loosely bounded electron from an isolated gaseous atom. Ionization energy is also called as ionization potential because it measures as the amount of potential needed to remove the most loosely held electron from the gaseous atom. The experimental value of ionization energy are determined either by spectroscopic method or by passing an electrical current of gradually increasing intensity through the vapor of the element in a discharge tube. It is expressed in the term of either kilojoule mole or electron volt atom. Thus, the ionization energy gives the easily with which the electron can move from an atom, evidence the smaller value of the ionization energy, the easier it is to remove the electron from the atom. Further, on which ionization energy depend. The magnitude of the ionization energy of an atom depend on following factors. Size of the atom. The ionization energy depend on the distance between the electron and the nucleus. Size of the atom. The attractive force between the electron and the nucleus is inversely proportional to distance between them. Continuously, as the size of the atom increases, the outer electrons are less tightly held by the nucleus. As a result, it becomes easier to remove the electron and therefore ionization energy decreases with the increase in atomic size. Second, charge on nucleus. The attractive force between the nucleus and the electron increase with the increase in number nuclear charge. This is because the force of the attraction is directly proportional to the product of charge on the nucleus that on electron. Therefore, with the increase in nuclear charge, it becomes more difficult to remove electron and ionization energy increases. Third, screening effect of the linear inner electron. In the multi-electron atom, the outermost electrons are shielded or screened from the nucleus by the inner electron. This is known as shielding or the screening effect. As a result of this, the outermost electron does not feel the full charge of the nucleus. The actual charge felt by the electron is termed as effective nuclear charge. The effective nuclear charge is the total charge minus screening constant, where the screening constant take into the account the screening effect of the inner electron. If the number of electrons in the inner shell is large, the screening effect will be large. As a result, the nuclear electron force will be less. Consequently, ionization energy will decrease. Thus, if other factors do not change, an increase in the number of electrons friend to decrease the ionization energy. Fourth, penetration effect of the electron. If it is well known that in the case of multi-electron atom, the electron in the s orbital have the maximum probability of being found near the nucleus, and this probability goes decreasing in the case of p-d-f orbital. In the another word, the s electron are moved penetrating toward the nucleus, and then p electron and penetrate power decrease as given in the cell in order of SPDF. Now, if the penetration of the electron is more, it will be closer to the nucleus and will be held firmly. Continually, ionization energy will be high. This means that ionization energy increase with increase in penetrating power of the electron. Thus, for the same cell, the required ionization energy would be more to remove an s electron than the to remove the p electron, which in turn will be more than that of removal of d electron, and so on. Fifth, electronic arrangement. The ionization energy also depend of electronic configuration of the atom. It has been observed that certain electronic configurations are more stable than the other. For example, half-filled and completely filled shall have extra stability associated with them. Constantly, it is difficult to remove electron from these stable configuration, and ionization energy is high. It may be isolated by the following example. The noble gas have the most stable electronical configuration in each period and have the highest ionization energy. The electron like beryllium, magnesium have the complete filled orbital and their ionization energy is large. The element like nitrogen, phosphor has the configuration in which orbital has the subshell are actually half filled and also stable, hence they are large energy to remove electron. Their ionization energy are high. Thus, more stable the electrical configuration, greater is the ionization energy. Variation of ionization energy in a periodic table. Ionization energy provide another example for understanding the periodicity among the electron. The ionization energy of element S, P block are taken in table 10. The variation of the first ionization in energy of the electron will with the atomic number up to atomic number 60 is given in figure 5. It can be seen that the figure 5 has that in the each period the maxima are found at the noble gas while the minima are found at alkali matter. Thus the metal group of group first have with one electron are outer s block orbital can be easily ionized while the noble gas with the ns2 and p6 configuration are mostly difficult to ionize. The following periodical trend has been observed. A variation among a period. In general, the ionization energy increase with increasing the number in period. This is quite clear from the value of ionization energy of second row element on the table 11. The generally increase among a period can explain on the basis of atomic size and nuclear charge. We know that on moving across a period from left to right, the nuclear charge increase. The second, the atomic size decrease among the period, truly energy level remain same. As the consequences of increasing nuclear charge and simultaneously decrease in atomic size, the valency electron are more and more tightly held by the nucleus. Therefore, more and more energy is needed to remove the electron, and hence the ionization energy keep on decreasing. However, so irregularity in their journal trend has been noticed, and these are due to half filled and completely filled configuration which have extra stability. To insulate this, let us consider the variation of ionization energy in the second period going from one element to another. Lithium to barium. On moving from lithium to barium, there is increase in ionization energy is due to increase in nuclear charge and smaller atomic size. From barium to boron, almost the nuclear charge of B is more than the Be, and wet there is slightly decrease in ionization energy from barium to bronze, and this is due to that fact. First, in the boron, the last electron has 2p orbital, which is at least slightly higher energy than 2s is easily to removed. The electron configuration of B is less stable than the Be, which has completely filled orbital. As a result, 2p orbital of B do not slightly held by the nucleus as 2s electron of Be. Hence, the ionization energy of B is less than the Be. B to C, boron to carbon to nitrogen. As we know that from boron to carbon to nitrogen, the ionization energy keep on increase due to increase in nuclear charge and decrease in atomic size. Nitrogen to oxygen. Oxygen, the element next to nitrogen, is slightly smaller ionization energy as compared to nitrogen. This is due to the fact that electric configuration nitrogen atom in which the 2sp is half filled is more stable than that of oxygen. Therefore, ionization enthalpy of nitrogen is more than that of oxygen. Oxygen to fluorine to neon. Ionization energy of oxygen to fluorine to neon because the increase in nuclear charge, decrease in size. Neon is a noble gas has maximum ionization energy in the period due to stable electrical configuration. Similarly, the variation in the energy of element of third period has been observed. B. Variation down a group. Within the group, there is gradually decrease in ionization energy in moving from top to bottom. This is clear from the ionization energy value of the element of the first group as given in table 12. This This decrease in ionization energy down a group can be explained in terms of net effect of the flowing factor. First, going from top to bottom in a group, the nuclear charge decreases, therefore gradually increase in atomic size due to the additional many shell. Third, there is an increase in shielding effect on the outer electron due to an increase in number of inner electron. The effect of increase in atomic size and the shielding effect is much more than that of the increasing number nuclear charge. As a result, the electron become less and less finely held to the nucleus as we move down the group. Hence, there is gradually decrease in ionization energy in group. Successfully, the ionization energy the atom may not be only lose one electron but more than one electron also. Therefore, it is essential to specify the definition ionization energy for each electron which can be removed. The energy required to remove a subsequently electron from the atom in the gaseous state is known as successive ionization energy. The first, second, third ionization energy refer to removal of first, second, third electron respectively. These change may be represented as flowing. Here, the ionization first, ionization energy second, ionization energy third represent the first, second, third ionization energy respectively. For the example, the first and second ionization energy of lithium may be as given below. As you can see, the second ionization energy is much higher than that the first ionization energy. This is due to the fact that the removal of first electron, the atomic change in the monovalent positive ion in the ion, the number of the electron decrease but nuclear charge remain the same. As a result, of this, the remaining electrons are held tightly by the nucleus, and it becomes difficult to remove the second electron. Hence, the value of second ionization energy I2 is greater than the first ionization energy. In the same way, the removal of electron, which result in formation of a dipositive ion attraction between the nucleus and remaining electron, increase further. This result in higher value of third ionization energy than the second. Successive ionization energy of the first 14 element are given in table 13. The ionization energy to the right of the stepwise line corresponding to removal of electron from the field configuration of the atom. As it is clear from the table, from each atom there is a larger increase in energy after all the outer electron has been removed. For example, in the case of sodium, the first ionization energy corresponding to removal of the valence is 496 kilojoule per mole. But the second ionization energy corresponding to remove the electron field electronic configuration is 4564 kilojoule per mole. Similarly, for magnesium, the first ionization energy is 737 kilojoule per mole and the second ionization energy is 1447 kilojoule per mole. However, the third ionization energy is 7738 kilojoule per mole, which is 5 times that of second ionization energy. This is because after all these electron in the shell has been removed, the next electron must be removed from the core of the atom have the stable noble configuration. Therefore, the ionization energy become higher. Electron infinity. As as the energy just as the energy is required to remove electron from the atom, the energy is released when as the electron is added to a neutral atom. This is called electron infinity. The amount of energy released when an electron is added to an isolated gas is called electron infinity. The process can be expressed as the definition implies, the magnitude of electron infinity measure the ability of an atom to hold an additional electron. If an atom has more tendency to accept an electron, large energy will be released constantly. The electron affinity will be higher. On the other hand, if the atom has less tendency to hold the electron, small amount of energy will be released, leading to the small value of the electron infinity. Electron infinity can be positive or negative. When the energy is released during the addition of electron to atom, the electron infinity is positive. Electron infinity are expressed in kilojoule per mole factor on which electron infinity depend. There are the many factors which govern the electron infinity, but the following are the some important factor on which it mostly depend. First, nuclear charge. In the electron infinity increase as the nuclear charge increase. This is due to the greater attraction of incoming electron if the nuclear charge is higher. Second, size of atom. With the increase in size of atom, the distance between the nucleus and the incoming electron increase, and this result in lesser attraction. Continuously, the electron affinity will be decreased. Electrical configuration. The element have stable electronical configuration of half or completely filled valence subshell, show well small tendency to accept additional electron, and thus the electron affinity are low or almost zero at certain cases. Periodic trend. Due to lack of sufficient data, the changing trend in the electron infinity on moving from the periodic table is less well defined than those of ionization energy. However, it has been observed that the electron infinity in general increase from left to right in a period and decrease from top to bottom in a group. These variations are discussed below. Variation down a group. On moving from down a group, the atomic size and nuclear charge increase, but the effect of an increase in atomic size is much more pronounced than of the nuclear charge, and thus the additional electron fell less attraction by the large atom. Continuously, the electron infinity decrease. This is clear from the decrease of electron infinity in going from chlorine to bromine and from to iodine. Variation in period. On moving across a period, the size of atom decrease and nuclear charge increase. Both of these factor into the great attraction for the incoming electron. Therefore, the electron infinity in general increase in the period as we go from left to right. However, certain irregularities are observed in the general trend. These are mainly due to the stable electron configuration of the certain atom. There are some important fact feature of electron infinity of element. These are: halogen has highest electron infinity. The electron infinity of halogen are highest. This is due to the fact that halogen has generally electron configuration of ns2 and p5 has only one electron less than the stable noble configuration. Thus, it has very strong tendency to accept additional electron, and therefore electron infinity is higher. Electron infinity of noble gas is zero, while of those of beryllium, magnesium, nitrogen, phosphor are almost zero. The electron infinity of noble gas is zero. This is because the stable electron configuration and thus has absolutely no tendency to additional electron. This means that incoming electron does not feel any attraction for the nucleus. Thus, no energy is released, and their infinity electron infinity is zero. Similarly, low electron infinity value of beryllium, magnesium, nitrogen, phosphor can be explained due to extra stability of the field 2s, 3s in the beryllium and magnesium respectively, and of half field of 2p and 3p in the nitrogen and phosphor respectively. Therefore, their configuration show a little tendency to gain the electron, hence their electron infinity is almost zero. Electron infinity of fluorine is unexpectedly less than the chlorine. As already explained, the electron affinity in generally decrease from top to bottom in a group. However, it is observed that fluorine is unacceptably less electron affinity than the chlorine. The electron affinity value of halogen are shown in figure 7. The lower the value of fluorine atom is due to very small size of fluorine atom. As a consequence of small size, there is a strong inter electronic repulsion in the relative compact sp subshell of fluorine, and thus increasing incoming electron does not feel much attraction. As a result, the electron affinity value is small. On the other hand, the electron affinity of chlorine atom is larger than fluorine, where the electron added is to be related in the large 3p orbital, which can be easily accumulated the additional electron. It may be noted that in general the electron affinity for some third periodic element are greater than the corresponding second period member. This is due to the smaller size of atom. The second period element which would be produce large electron repulsion for additional electron. This effect is much more pronounced in the smallest fluorine atom to discuss above. Successive electron infinity like the ionization energy, second and higher electron infinity are also possible. However, the second electron is added to negative charge ion, and the addition is opposite to the Coulombic repulsion. The energy has to be supplied to force the electron as below by the oxygen. In another word, the second electron infinity would be negative value, since the first infinity in which energy release is positive. For example, the first and second electron infinity of oxygen and sodium are electronegativity. Electronegativity. When a covalent bond is formed between two homologous atoms, the shared pair of covalent and bond lie extremely midway, but the nucleus of the two atoms, because both of the atoms may be have same attraction of these electrons. For example, in the molecule such as hydrogen, chlorine, fluorine, the electron pair remain actually half distance between the two nuclei. However, in the case of covalent bond between the dissimilar, the electron pair may be closely to the atom than the other. This is due to the fact different atom has different tendency to attract the bond pair of the electron toward itself. The tendency of an atom to attract the shared electron pair in a molecule toward itself is electronegativity. Different atoms have different tendency to attract the bonded pair toward themselves. Greater the ability to of an atom to attract the electron in a bond, larger is the value of its electronegativity. It must be remembered that unlike other atom properties such as ionization energy, electron affinity, which are relative to the individual gas atom, the electronegativity is related to the atom in their bonded state. There is no directed method of measuring the electronegativity. However, various attempts has been made to drive a scale of electronegativity for the element. Some of these are discussed below. Pauling scale of electronegativity. In the 1932, Pauling was the first to pose a scale of electronegativity. He proposed that the scale based on the bond energy in heteronuclear bond. He suggests that if the two atoms A and B has the same electronegativity value, the bond energy of the A and B bond will be equal to the geometrical, means the bond energy of A and BB bond. For example, the bond energy of AB molecule will be written as EA is equal to EAB is equal to EAA into EB bracket half. This relation is based on the assumption of pure covalent bond of A2 and B2 and the AB molecule. However, he observed that for the most of AB bond, the actual bond energy is more than the geometrical means the bond energy of EAA and EBB. This means that the two participation atom has different tendency to attract the shared pair has a different electronegativity. In another word, the AB bond has no longer be purified covalent bond. As a result, there is contribution of ionic structure. AB plus and B negative assumed B is more electronegative than A in addition to pure covalent AB bond structure. The difference between the actual bond AB and B and the geometrical means bond energy is known as excessive bond energy. It is measured by difference in the electronegativity of the two atoms A and B. The excessive bond energy arises due to the resonance between the structure A and B, and the A plus B negative is known as ion resonance energy. By calculating electronegativity for different bonds, the pooling suggests the flowing type of relationship between the electronegativity of two atoms XA and XB and the excess bond energy the where the ionization electronegativity is excess bond energy is in kilokelvin mole. It may be noted that constant value 0.18 is valid when the bond energy of EAA and EBB is kilomole. When the energy is in ev per mole, the relation become xa minus xb is equal to 0.208 electronegativity root. The SI unit of the relation become xa minus xb is equal to 0.088 ionization energy root. There would be carefully is using this relation terms the bond energy should be taken in consideration. Assigning an arbitrary value of an element, the electronegativity of the other element could be easily calculated. The pooling assigned the value of 4 in the most of electron element of fluorine. The pooling electron value in the table 15 for the normal element. They are most commonly used value. Disadvantage of the pooling scale of the electronegativity. The main disadvantage of the pooling scale is that the bond energy are not known with good degree of accuracy for many elements. However, the value of relative are relative values. Mulkeen concept of electronegativity. Mulkeen suggests that the tendency of an atom to complete four shared pair of electrons in a bond should be average ionization energy and the electron infinity. Thus, according to the Mulkeen, electronegativity of an atom is equal to ionization energy plus electron infinity divided by 2. Both the ionization enthalpy and electronegativity are positive value. The physical picture of Mulkeen concept is resembled because the tendency of the one atom to attract share electron is bounded should be average tendency of the atom to hold its own electron and tendency to attract the additional electron. The Mulkeen value has been found to be about 2.8 times as larger as Mulkeen value. Therefore, these values are divided by the 2.8 to get the pooling value. However, if the ionization energy and the electronegativity will be expressed in kilojoule, then the 1 eV is equal to 1.602 into 10 k power minus 19 into 6.0222 into 10 k power 23 is equal to 96.48 kilojoule per mole. The Pauling can be expressed as disadvantage of the Pauling scale of electronegativity. There are the two disadvantages of this scale. Electron infinity value has only few electrons are known. Second, the electron ionization enthalpy and electron infinity value change with the valence state of the element. Aldred and Rokow scale. This concept is based on electrostatic force of attraction between an atom and its nucleus. This force of attraction is taken as measure of its electronegativity. The force of attraction between the nucleus of the atom and its valence electron are governed by Coulomb's law and given as the force is equal to Ze by R square. The effective nuclear charge can be easily calculated by using the Stellar rule for scanning of inner electron. The force calculated for the above the equation were plotted against the Pauling scale, and from this plot the following relationship is obtained. Known the value of Z and R, the electronegativity of any element can be calculated. Disadvantage of alert and rose scales. The main disadvantages are: first, covalent radii of many electron elements are not available. Second, the Stellar rule for calculating the effective nuclear charge are empirical. However, this scale gained importance because it does not contain the quantity such as electron infinity, bond and dissociation energy, which is known for the comparatively less number of elements. Sand-Sun scale of electronegativity. Sand-Sun propose a scale of electronegativity based on the compactness of the electron cloud around the nucleus and average electron density of the atom. The average electron density of atom may be given as D is equal to 3Z by 4 pi r square. According to Sanderson, the electronegativity is expressed as stability ratio for an atom. The stability ratio is defined as the ratio of average electron density of an atom that of individual electron density of hypothetical isoelectronic insert gas atom. Thus, the SR is equal to D by Di. D is the electron density of an atom. Di is the individual electron density of a hypothetical noble gas given the same number of electrons. The stability ratio of the atom is measured by electronegativity. The SR value for the similar electronegative value obtained by the Pauling. This is or are justified to the Pauling electronegativity by giving the equation. It may be noted that the none of the electronegativity scale discussed above has a distinct advantage over the other. For the comparison, the electronegativity value calculated by the Weiss method as given by table 16. However, the Pauling scale has been completely used, and in our further discussion there will be value will be used. Mulkins and Zephyr scale. Mulkin and Zephyr has also proposed a new scale which has take in account the role of hybridization while calculating the electronegativity based on ionization and energy and electron infinity. However, it has been discussed in present text. The factor affecting the electronegativity. The electronegativity of an atom is not fixed quantity but depend on the large number of factors both of the isolated as well as bonded atom. Some of the important factors affecting the electronegativity value are ahead. First, oxidation state. The electronegativity of an atom vary from bonding state to another depending upon the oxidation state of the another atom in the molecule. In general, the electronegativity increase as positive oxidation state of the atom increases. This is obviously because with the increase in positive oxidation state, the tendency to attract the electron will increase. For example, Pauling electronegativity value for Tl is 1 0.62, where it is about 2.044 TL third. Some example are 4 and 9. However, electronegativity decrease with the increase in electronegative charge of the anion. This is due to the fact that the more the electronegativity charge ion will be more attract less the electron than it less negatively charged ion. Type of hybridization. The type of hybridization also affect the electronegativity of an atom. We have to learn that the orbital has never to the nucleus than PDF orbital because of their higher penetration power. Therefore, the s orbital will be have greater electron attraction power or electronegativity. In another word, the electronegativity increase in S character of the hybrid orbital. This can be easily isolated by taking the example of carbon. The S character increase in order of CH4C2H4C and C2H2, and the electronegativity of these compounds are also increased. Similarly, for the nitrogen atom, the value of electronegativity are 3.68, 3.94, or sp3, sp2, sp hybridization respectively. The nature of substitute. The electronegativity of a group vary from the nature of the the substitute. This is due to inductive effect of the substitute. For example, CH 3 is 2.30, CCl3 is 3.30, and CF3 is 3.35. In this case, the electronegativity of this group will be electronegativity of F carbon as it adjusts by presence of substitute. This value may be based on dipole moment after the electronegativity and kinetic data. Periodic variation of electronegativity. The electron negativity generally increase on moving across a period from left to right, and this is primarily due to decrease in atomic size and increase in effective nuclear charge. As a result of this, the increase in effective nuclear charge, attraction of the electron will increase. Electronegativity generally decrease from top to bottom of the group as atomic size increase and the bonding electron become always from the nucleus. Thus, the alkyl metal of a group first has the lowest ionization electronegativity, and the halogen group of seventh have highest electronegativity. Further, the inspection table 2.14 showed that the non-metal on the right hand side of the periodical table have highest electronegativity, while the metal on the left side of the periodical table have the lower electronegativity. In general, as an appropriation, the element with electronegativity 2 or greater are non-metal, while those of lesser than 2 are metal. It is clear from table 14 that the electronegativity generally increase on moving across a period from left to right and decrease as moving from down a group.